Okay, so for the last thing in our energy unit, we're going to talk about mechanical advantage and efficiency. Now, a mechanical advantage is exactly what it sounds like, the advantage you get. Efficiency is how we measure that mechanical advantage. But let's get into it a little more. So when I talk about mechanical advantage, basically I'm talking about simple machines. Like, remember our rope and pulley here? Well, with that rope and pulley, that means that we get an advantage out of using this. There's a reason we want to use that machine. It often multiplies the force. But like I said, this trades off with distance because it's the same amount of work that is needed. So you're able to do the work with less force, but get the same results. That means that with the proper pulley, I could very easily by myself, not easily, but I could by myself lift an elephant, right? The difference is the amount of rope I might have to pull down to get this elephant to move just a little bit up might be greatly different, okay? But I would still have that mechanical advantage because I'm getting more upward force than I'm putting into the rope, and that's a mechanical advantage. When it comes to mechanical advantage, there's actually two different types. There's actual mechanical advantage and ideal mechanical advantage. First, we're going to look at the AMA, the actual mechanical advantage. Now, as we said before, with mechanical advantage, we're talking about getting more force out than we put in, right? And so it, with actual, actually looks at the force ratio. Now, both of our mechanical advantages are not going to have units because they're ratios. It's just how much is in to how much is out, basically, okay? Or in this case, how much is out opposed to how much is in. With this, you need to think about the fact that it's a force of resistance. That's what the R stands for, is just the output force, okay? So how much force you get out of your machine opposed to how much force you put in that we call the force of effort. So think your effort's what you put into things. Resistance is what you get out, okay? So the force out divided by the force in will give you your actual mechanical advantage. So if I was doing this little problem, what is the mechanical advantage of a machine that uses an input force of 400 newtons to create an output force of 1600 newtons? Well, all I'm going to do, let me get my pen here, I'm going to say that that's an AMA, and it's going to be equal to that force R, or force out, which we said is 1600 newtons, divided by the force in, which is 400 newtons. And that's going to go in there 4 different times. So that's my answer. I don't have any units with it because it's just a ratio. Remember, ratios. That's just that right there. Now, ideal mechanical advantage can be a little bit different. Ideal means this is how much you would guess the advantage would be. But because it's a guess, it's done with just measuring distances. So notice I have something here which is like a lever arm, right? I have my fulcrum, my lever arm, and I have a place where I'm going to put in energy and where I'm going to get out, right? So there's a distance of the part that I'm going to put in my force on, right? The distance of that side is the DE, our distance of effort arm, okay? On the outside, where I'm going to get it out, so hopefully I'm lifting a boulder somewhere right here on this end. Think about that as getting my force out. The distance from the fulcrum to that point is my distance of resistance. Now, ideal is just looking at the ratio of those distances, and this time it's the effort over the resistance. So it's what I put in divided by what I would get out. Another way to think about this is, so if I lifted it straight up, so let's say I'm using a ramp here. If I lift it straight up, that's what I would have to do, the distance I would have to move it, if I didn't have the ramp here to use, right? So that's my resistance because it's what I'm getting out of it. It's what I hope to accomplish with the distance here. I just want it up 2 feet. Now, my distance of effort is once I use the ramp, I'm reducing force, not distance. So it's going to be a greater distance I move it. So this 20 feet is the length that it would take me for my effort to be put into the machine of the ramp. I get out of it 2 feet up, but I'm putting into it 20 feet across at an angle. And so that's how this ideal mechanical advantage works. And again, ideal means it predicts how well the ratio would be if it was a perfect system, right? And so your ideal is like, okay, I'm not going to lose any energy whatsoever to heat or sound or any of that stuff, okay? So that brings us to the idea of efficiency, because we need to measure how well a machine actually performs. And so this is really just the ratio of useful work performed by a machine when we're looking at its overall ability to do things about energy expended towards the task opposed to the heat or sound or whatever it might give energy off to. So it is a ratio, even though we are looking at work, okay? Because this is going to be joules out, joules in, and when you divide joules by joules, they cancel out, and so multiplied by 100%, that percent gives us a percentage. And this should make sense. You probably have talked to somebody and said, well, I'm not feeling 100% today. Well, that means that you're doing perfect. You're a machine that consumes fuel or food, fuel, and produces some sort of work. And so there's certain days where we might be fighting off a cold or something. You're using energy to fight off the cold, so you're not 100% of yourself. It's the same basic thing for simple machines, okay? But we need to understand a little bit more what we're talking about when we say work out and work in, okay? So if you're talking about, let's say a ramp real quick. If I have a ramp, right? So my goal of the ramp is to get some sort of heavy object, let's say that's a heavy box, up a certain height, all right? Now, I could pick that box straight up and get it to that height that I need, but that wouldn't use the machine in any form. So that's what I'm hoping to get out of this machine is the end result of not using the box. So if I had to pick the box just straight up and move it whatever this height is, so that would be a force across a distance, which is indeed work. That would be the work I'm hoping to get out of this machine. I want it to do what I could do myself, but it would be really hard. The work in, however, let's see if I can erase some of this stuff. Yeah, so the work in, if I'm talking about that, is the amount of work you use with the ramp or with the simple machine. So now we're talking about the distance here and the force that you apply there, which should be less than if you had to lift it straight up, right? Now the distance will be greater, but the force should be less. And so that's the advantage you're getting in that machine. And that's why we use force or distance when we're talking about mechanical advantage. But now we're looking at the combined use of those to get the work in. The work in, it's what you're putting into this machine, the simple machine of a ramp, okay? Now, so the work you put in is probably going to be greater than what you get out. Therefore, it's out divided by in times 100%, okay? Now, that's just one example of a simple machine, but it's used for all kinds of things. I have an example here of batteries being charged. Now, if you're not familiar with rechargeable batteries, like AA type batteries, that's fine. Think about it as your cell phone battery, okay? It's a rechargeable battery. So you use a charger, and it uses 173 joules when charging a AA battery. Only 0.7 joules actually is used by the battery. So that means a lot of that charge is going to other things. And if you think about this, you've experienced this. I used to have an old laptop that when I charged it, it heated up really, really hot. Well, that's because a lot of the charging energy wasn't used well by the battery in the laptop, and it went to heat instead of to what I needed it to go to, just charging the battery and running my computer. Same thing here. So the amount you're putting in is not the amount that it's actually accepting. It's not getting our goal. And so this bigger number is what we're putting into the system. That's our work in, okay? And so we would end up having our 1.73 joules and on the bottom, and on top we would have 0.7 joules for what we're actually getting out of the system. Notice these joules are going to cancel out, so it no longer has the unit of joules, and then we're going to multiply it by 100%, and we're going to get that the efficiency is somewhere around 40.5%. Now look at that. That's not even half. So that means that a whole bunch of the energy we put into this is getting lost to heat or causing other things to go on. Actually, on a battery, I'm not sure where it would go other than heat unless it's sparking out. So it might be causing some light there, but probably a little dangerous. However, you can see that efficiency tells us how much is actually doing the task that we want, and it's always done in a percentage, okay? And so that's how you do efficiency.